Hello, so this is part D of homework 3. What we're going to do right now is we're going to derive the Laplace transform of a time-shifted function with dead time in respect to theta. And then we're going to determine the Ziegler-Nichols ultimate controller gain and period for a first-order system with dead time of 0.1 seconds, time constant of 1 second, gain of 1. And then we're going to simulate this in Colab of the closed loop response of the system utilizing that Ziegler-Nichols PI controller parameters. And we're going to do the same thing using the Smith-Corripio ITAE open loop tuning method. So first what we're going to start with is just we're going to draw this graph. So in terms of 0 for our time shifted function, kind of bad, and then we're going to go ahead and draw another chart which kind of converges, and then what this represents is that dead time. So the distance between is theta, but this line right here is the dead time that we're referring to. So in terms of our function, this essentially just equals our u t minus theta and then f t minus theta. And if we take the Laplace transform of this function, just going to write it down. What we find is we're going to derive this in terms of 0 to infinity, and we're going to get theta f minus theta. We're going to multiply this by e to the negative st in terms of t. However, we want to state that theta in this case, or sorry, tau in this case is equal to t minus theta. And since we also have a t right here, we're going to go ahead and substitute that for tau plus theta. All right, so now utilizing our information that we found about tau, we can go ahead and convert this. However, one thing to note, instead of taking it in terms of 0, we're going to take it in terms of negative tau, or negative theta. We're going to say our u tau f in terms of tau, and then we're going to have e times s tau plus theta, and we're going to take this with respect to tau. And then how do we get this back to 0 is because we want to that any time when tau is less than 0, our u tau function will be equal to theta. So I'm going to go ahead and convert this back to 0 to infinity, and then just basically rewrite this, and we're going to break up our e, make it easier to solve. And then now we can take the Laplace transform of this, and if we solve this section right here is basically canceled out, and we can use this as our f function. So our Laplace transform, this right here will essentially just be e times negative, or e to the negative s theta times the Laplace transform of function f. And now we can utilize this, and we can go ahead and simulate our closed loop response. Okay, so this is the coding section. I've already gotten our library set and then got our values that we require for this, and we're going to go ahead and start with the Ziegler method. And yeah, let's go right into it. So we're going to have to find our GP value, which is the KC times 1 plus 1 divided by tau I times S. GC will equal our okay, and then so I actually switched around the GC GP. It's supposed to be GC, and then GP is K times R. Yeah, K times exponent of, or no, it's negative theta times S divided by our tau times S plus 1. Yep, and then we're going to have our G closed. This is GC times GP divided by one plus GC times GP. And we're going to go ahead and define our T and H. That's how we're going to simulate our closed, and then lambda in terms of T to 1. And then we're going to have N equals 1000, and our dt is, I believe it's 0.01. Might be 0.1. I have to double check that. And then, does that work? Yes, it does. And then we're just going to go ahead and make our subplots. Dot add underscore scatter x is t, y is h, and mode lines. And then want to just add a little fig dot update underscore layout. Is 400, and yep, so there we go. So in this graph we can actually see that our peak, it starts off pretty unsteady in our system, but after a while it kind of mellows out and it's back to steady state. One thing to point out is in class we learned that this peak is going to be 4 times larger than this peak, and then this one is going to be 4th of that, and then that little tiny peak over there is also a 4th. So then it just decreases by a factor of 4 in terms of oscillation before going into steady state. Okay, so now that we had our Ziegler-Nichols ultimate controller gain done, now we're going to apply pretty much the same thing but to the Smith-Caripio ITAE open loop tuning method. So I've already gone ahead and put in the values that we need that Carlos provided. So go ahead and define y, which this is PA times theta divided by tau to the PB. Kc is just y divided by k, and then or tau I is just tau divided by IA plus IB divided by theta divided by tau. Just want to see if that works. Yes, it does. And then what we're going to do is basically just copy down this entire thing, since we are utilizing the same exact sequence. However, the tuning method just changes our controller gain and our tau. Oh, there we go. So kid and okay, so this is just one little small error. This is a multiple sign. There we go. And so we can see there's a drastic difference between this graph and this graph. So we can see the tuning method has definitely worked. And comparing, we can see that we don't really have oscillations, especially a spike above 1.5, whereas here we can see that it kind of just, it doesn't really spike too much. You can see there's a tiny bump, but it's better than that. So looks like the tuning method definitely worked in terms of immediately, or at least almost immediately, going into a steady state for the system rather than oscillating and then reaching our steady point. So that concludes for part D. And yep.